One of the major themes in grade 12 physics is energy. When we're talking about energy in our mechanics unit, we're looking at work. How much work do you need to do in order to change an object's motion? And we calculate that in terms of joules. When we're looking at space and looking at orbits, again, it comes down to energy. In fact, in space, everything comes down to energy because you're dealing with so much faster speeds and so much bigger distances. So we've looked at potential energy and kinetic energy. So let's look at our formulas for these again. Kinetic energy, you may recognize, we've used that before. Now, our potential energy, when we're looking at gravitational potential energy on or near the surface of Earth, we usually use our potential energy due to gravity is equal times the mass times g, or 9.81, times the height, or the height change above the surface of Earth. When we're looking at in space, we might not be orbiting Earth, or we might be much further away. So we use this formula instead. Notice that the g in this case, capital G, is the same constant as from the last video, which is 6.67 times 10 to the negative 11. And the radius is not squared on the bottom. When we derive this formula, that radius does disappear. Our kinetic energy, we're used to that formula as well. It's half mv squared. That's a very common formula. When we're talking about potential energy and kinetic energy, one of the things that is useful when talking about space is that we can talk about how much energy an object needs to leave Earth. This is called the escape velocity. In other words, if I were to get an object moving fast enough that it would permanently escape Earth's gravity and it would never return. Any slower than this, and the object will eventually slow down and return to Earth. Any faster than this, and it will never do so. It will continue moving away from Earth. We can figure this out by realizing that in order to escape Earth, our kinetic energy must be greater than our gravitational potential energy on the surface. We can combine these two formulas, and through the magic of algebra, we can derive the formula for escape velocity, which is this. Escape velocity is the square root 2 times g, 6.67 times 10 to the negative 11, times the mass of Earth divided by the radius of Earth. This is for an object at rest on the surface of Earth. Now notice if you're using this for another planet, say you wanted to leave Mars, you'll use the mass and radius of Mars. This formula is fairly straightforward. Note, this formula is how much speed, or will give you the velocity you need to completely escape Earth. This is not a constant velocity, and this does not account for acceleration or deceleration or anything like that. This just says, if I throw a ball up this fast, it will leave Earth. One other thing to note is that this is not the velocity you need to get to space. If I want to get to space, you could, theoretically, climb a ladder and get to space. You can go up the ladder at maybe 0.5 meters per second, and eventually you will get into space 100 and something kilometers up. It will take you a long time, and you'll be very tired, but you can do that. But notice you will not have escaped Earth's gravity well. A little bit different concept. When we're talking about escape velocity here, and when we're talking about trying to escape Earth's gravity well, we also have a couple other formulas we can look at. If I have an object at rest on the surface of Earth, the only energy that I'm concerned about is the gravitational potential energy. This I can find by this formula here, my gravitational potential energy formula. That is the total energy that this object has. It does not have kinetic energy relative to the Earth because it is not moving relative to. When I look at an object in orbit, I can find the total energy by this formula. Notice this is a little bit different. First off, notice that we have the orbital radius, which is the distance from the center of the Earth to the center of the object orbiting Earth. That's the moon. It's the center of Earth to the center of the moon. That is important. When you're looking at these centers between objects, you need to add in the radius of these frequently. If I say the International Space Station orbits 100 kilometers above the surface of the Earth, that's great, But remember, there's an additional 6,000 and some kilometers to the center of the Earth that you have to add in. This formula we can also derive from our kinetic energy formula and our circular motion formulas to find our total energy for an object in orbit. I'm not going to show those derivations right now. It's also important to note that the change in energy is what is actually relevant to us. I'm not so much concerned about our total energy either in Earth or on Earth or in orbit. I am concerned about how much energy I must add in order to get into orbit. How much velocity I must add. This is our change in energy, or delta E. We frequently also talk about this in terms of change in velocity, or delta V, which we can find by using our velocity formula, our kinetic energy formula. This change in velocity or change in energy tells you how much you're going to need to speed up or slow down in order to change your orbit, get into orbit, to leave orbit, or to transition to a different orbit. For example, if you want to go to Mars, you need to change your orbit from the orbit of Earth to the orbit of Mars. In order to do that, you can use something called a Hohmann transfer orbit, which is a very efficient way to do that. But you still must put in enough energy transition between those two orbits. Orbital mechanics and orbital energy is a little bit confusing, and there are a bunch of formulas with it. These are a couple of them, and I hope this has helped. Have a great day.